Okay guys, in this video we're going to be talking about collision theory, and our main goal is to, first one of our goals is to learn about the postulates of collision theory and how chemical collisions affect reaction rates. The idea being, in order for two molecules to react with one another, they need to hit one another. We'll also look at the temperature dependence of the reaction rate. And so this is what the Arrhenius equation is all about. And the Arrhenius equation involves an important idea called the transition state and the activation energy. And so we'll talk about those concepts as well. And so here, just the main idea, in order for reactions to occur, reactant molecules need to collide with one another. So in some sense, the reaction rate should be proportional to the rate of collisions, or the so-called collision frequency. Now there's a little bit more to it than that, because molecules are not just point particles. They have a shape, and they have different sides to them. And so for complicated molecules, something other than a monoatom, in order for the reaction to occur, the collision needs to take place with a proper orientation. And so here's just a graphical example of that. Suppose you're considering the reaction between carbon monoxide and oxygen. If the carbon monoxide collides with the oxygen in first, no reaction is observed to occur. But if the reaction occurs where the carbon end collides with the oxygen atom, then there's a chance for forming CO2 and releasing an oxygen radical. Okay, so this is the orientational or steric effect, as it's called. S-T-E-R-I-C, steric effects. Another thing that is very important, in fact, was probably more important for us, is that in order for the reaction to proceed, even if you've got the correct orientation, the two molecules need to have enough energy when they collide in order to overcome what's called the activation energy for the reaction. So what we have here in the diagram is we're plotting the energy of our reactants as a function of some fictitious, I wouldn't call it extent of reaction. It's probably not the best way to have described it. Probably the reaction coordinate would be the better way. So here, cross out the extent of reaction and replace it with the statement reaction coordinate. Which represents the minimum energy pathway that takes you from your reactants on this side of the graph to your products on that side of the graph. Okay, so the path that we're following, this reaction coordinate, it's the minimum energy path that takes us from reactants to products. Well, very often there is a peak in the minimum energy path. And so this peak is what we call the transition state of the reaction. It's a transient complex. Sometimes it's called the activated complex, that is unstable. Once reached, if there's enough energy left over, there's a good chance that you're going to fall apart and form the products. It can also go up and then come back down. So it just kind of depends on that particular collision. But there's a minimum amount of energy that's needed in order to exceed this transition state barrier. And that's what we call the activation energy. So going from the reactants to the transition state involves one activation energy. You can also go backwards. So you could go from the products. The products could collide with sufficient energy to overcome this barrier. The activation energy going the other way is a lot larger, right? It would go from the bottom, it would go from this point in the curve all the way up to the peak here. That would be the activation energy in the other direction. Notice that the delta H is labeled. So the difference in energy, really we should say enthalpy, between the reactants and the products, that's the enthalpy change. And so this diagram, this would illustrate an exothermic reaction, where we see that the reactants, the energy of the products is less than the energy of the reactants. I could draw a corresponding endothermic potential energy diagram where starting at the reactants here, we have a barrier, and then the energy of the reactants is higher. So here, delta H, if we put the sign in, here delta H would be greater than 0. For this one, delta H would be negative. We still have an activation energy in the forward direction, and then this would be the activation energy in the reverse direction. Okay, so it just depends on which way you're going. The temperature dependence of the rate constant. Okay, so the rate constant is called a constant because it doesn't depend upon the concentration of any of the reactants or the catalyst. It does, however, depend on temperature. And as we've said previously in a previous video, the rate of the reaction generally increases with temperature. And that increase in temperature is described by the Arrhenius equation, which is given right here. And so there's actually a couple of different forms of the Arrhenius equation that we're going to play around with. And it looks like I have them on the other slide, so I'll just wait on that. Let's just talk about the different parts here in the exponential form of the Arrhenius equation. So here you've got your rate constant. Okay, its units are variable, and it's equal to some frequency factor. Now the notation is a little confusing here because I've been using the following to represent the concentration of a generic chemical species. That's unfortunate because in the Arrhenius equation, this does not represent the concentration of anything. It's a separate quantity altogether called the frequency factor. Sometimes it's called the pre-exponential factor because it comes before the exponential factor in the Arrhenius equation. It's related to the collision frequencies of your molecules when they collide. So like how many collisions occur per unit time. That's why it's called the frequency factor. It has variable units depending upon the kinetics of the equation that you're describing. The next factor, the exponential itself, with its argument, is called the Arrhenius factor. So e to the minus the activation energy divided by RT. EA is the activation energy. It's usually expressed in kilojoules per mole. When you do that, you need to express the gas constant in kilojoules per mole per Kelvin. And T is the temperature in Kelvin. The Arrhenius factor, what it represents the fraction of molecules that have kinetic energy greater than the activation energy at a given temperature. Okay, so you have a fixed temperature. The activation energy is fixed. This exponential represents the fraction of molecules in your sample that have high enough energy to collide and overcome the activation energy. This is represented graphically here by these diagrams where we're essentially plotting the distribution of kinetic energies in a gas sample. So the number of molecules that have a particular kinetic energy. No molecules have zero kinetic energy. For a given temperature, there's going to be a peak. So most of the molecules have a kinetic energy around here. And then you see that as you go to higher and higher kinetic energies, the number of molecules with those higher kinetic energies drops down. Okay? Now let's suppose that our activation energy is this value. Okay? So you see that this would be for an activation energy that's very large, very few molecules. That's the shaded area under here, which represents which the Arrhenius factor represents, this shaded area. Very few molecules have energy greater than this particular activation energy. Now, if you were to lower the activation energy, so if this vertical line was to represent the activation energy for the reaction, then the area beneath the curve is represented by the Arrhenius factor, and you see that at a smaller activation energy, a greater fraction of the molecules in your sample are going to be able to overcome the barrier. There's also a temperature effect. So when you change the temperature, it changes the distribution of kinetic energy. So here's a low temperature. This red curve is a low temperature distribution. When you increase the temperature, you broaden the distribution function. And so you're at a given activation energy, when you increase the temperature, you're going to have more molecules that have kinetic energy greater than that activation energy. And so increasing the temperature increases the fraction of molecules that can overcome the reaction barrier. So that's the effect of the Arrhenius factor. And it's important that you understand how temperature and activation energy both affect the Arrhenius factor. There are alternate forms for the Arrhenius equation. So here I'll show you the math now. So we'll just do a fresh page. So here's the exponential form for the, what am I doing here? K equals a e to the minus ea over rt. Okay, so this is the exponential form. The linear form is also important, so we'll take the natural log of both sides. Natural log of a e to the minus ea over rt, like so. Use the rules of natural log to write that in the following way. This I like to call the linear form of the Arrhenius equation, because if you make this y, if you make this a constant b, this will be a constant m, and then you make 1 over t, your x variable, you get the equation for a line. So if you were to plot, for example, I think it's on the next slide here, natural log of k versus 1 over t. I didn't get it on there very well, so I'm going to draw another one. I'll draw it here. Natural log of the rate constant versus 1 over t. What you'll wind up with is a downward sloping line where the slope is equal to minus the activation energy over r. And the intercept is the natural log of the frequency factor. So what you can imagine doing is you can do your, let's say, your initial rate method that allows you to determine k at a given temperature. You then repeat all of those experiments at different temperatures and then plot the calculated value for the natural log of the rate constant versus 1 over the temperature. Do a linear fit. The slope is equal to minus the activation energy divided by r. So by doing temperature-dependent kinetic studies, you can determine the activation energy and the frequency factor using this linear form of the Arrhenius equation. Now, any 2 points on this line satisfy the linear equation, of course, and then so what you get next is what I call the two-point Arrhenius formula, which is right here. And so let's call this point here, this will be the natural log of k2, this will be the natural log of k1, this will be 1 over t1, this will be 1 over t2. These 2 points are connected by a line, and that's what I call the two-point Arrhenius equation. So look at this equation. Given the activation energy, given T1, T2, and K1, you can then solve for the new rate constant. Or given the rate constants at both temperatures, you can use that to find the activation energy. Okay, let's illustrate that with some problems here. Let me just take a quick look. Let's go ahead and do this one here. So you've got the rate constant for the decomposition of dinitrogen pentoxide is 1.66 liters per mole per second at 650 Kelvin, and it has a value of 7.39 liters per mole per second at 700 Kelvin. Assuming the kinetics are consistent with the Arrhenius equation, calculate the activation energy for this decomposition. So here we've got the two-point Arrhenius equation. Here, that's the gas constant. We know the 2 temperatures, we know the 2 rate constants. They want us to find the activation energy, so we need to rearrange it. To get the value. Let's plug in the numbers here. It's a little tight squeeze. Anyway, 8.314 times 10 to the minus 3. This will be kilojoules per mole per Kelvin. Don't forget the minus sign. Natural log of the 2 rate constants. Let's call this K1, T1, K2, T2. So it's going to be 7.39 divided by 1.66 divided by 1 over T2, 1 over 700 Kelvin, minus 1 over 650 Kelvin. Right, starting here with the natural log, 7.39 divided by 1.66 natural log times 8.314 to the negative 3. Make that negative, divided by quantity, 1 divided by 700 minus 1 divided by 650, close quantity. The minus signs cancel. We wind up with 1103. That's going to have units of kilojoules per mole. The 1 over Kelvins cancel that Kelvin. So this is the activation energy for this particular reaction. And we've used the 2-point Arrhenius equation to find it. Given that activation energy, we can go back to this equation and solve for the frequency factor. We would just take the activation energy, plug it here, and you could plug in either T1, K1 or T2, K2 to find the activation energy. I'm sorry, to find the frequency factor. Well, I'm going to go ahead and stop this video here. This will be a short one, and then we'll pick up with reaction mechanisms in the next video.